Okay, let's begin then. Welcome everyone to the Astronomical Society of Edinburgh and to our mid-month meeting. Here we go. This is what we've got coming up tonight. I've just got a few news items, what's coming soon, and then we have the main event of the evening. We've got how to be an exoplanet detector from Dr. Jo Barstow from Open University. Thank you, Jo, for joining us, speaking to us. Look forward to that. Yes, if you are on Zoom, then please mute your sound just now, please. We do have some new members joining us in November. Welcome to Pat, Grant, Alex, and Michelle. And our membership has now rocketed to 204. I don't know if any of you are on tonight, but welcome. The tough stuff. So yeah, your subscriptions were due on the 1st of October. A lot of you have paid already. Thank you very much. But there's still quite a number outstanding. As always, if you joined on or after the 1st of April this year, then you don't need to renew until next year. And we've decided not to increase our rates again this year. We've kept them pretty low for quite some time now, so it's still really good value. Yeah, as you know, we've been very involved in the comet section of the BAA with what we've been using our telescope in Spain for, and they have asked us if we would host their comet section meeting in 2025. So we've said yes to that, and that will probably be at our normal meeting place, the AUC in Edinburgh, on the 4th of October. And everyone's welcome to join that. Come to that. BAA people will be coming from all over the country, but we're obviously able to attend that, and any other people interested in the local area as well. I've been to a BAA meeting recently over the other side of Glasgow, and it was really good, worth going to. So that should be a good event, and I'll tell you more about that as we've got more information, but it's early days yet on that. Yes, Azero, a remote telescope in Spain. As you all know, we've embarrassingly not had it working for over a month now. Both our cameras failed. Um, but we have just were sent back to Omegon, who were very poor about communication and not telling us anything. So we didn't know when they were actually going to come back. But they are now on the way back. But unfortunately, we actually just ordered a third camera just to cover ourselves off. And the same day it arrived at Travinca, we got notification that the cameras that were being repaired or replaced are on their way back as well, which is rather expensively embarrassing. So we'll take a decision on what we're going to do with that. But it'll be great to get operating again. Hopefully within the next week, we'll have a telescope, which you can see arrowed there. That was from this morning. It's waiting for us with no cameras on. So we should have that operating again quite soon now. These are the talks we've got coming up over the next couple of months. So our next one is an in-person talk in Edinburgh from Dr. Rebecca Higgett. It's an interesting historical one about the Early Dial. So that should be good. So that will be in person at the Augustine United Church. It will be on Zoom for AAC members and on YouTube for any visitors who want to join us. On the 11th of December, we have our monthly Imaging Observing Group meeting. That's for members, and if you haven't been to one before, worth coming along to that. And that's where we all sort of learn together, share our experiences, our images, our techniques, and so on, and just generally have a good chat about astronomy. They're always really good fun. 20th of December, an online-only talk from Professor Martin Hendry about gravitational wave astronomy. I've heard him speak on this before, and he's a really good speaker, and that will be a good talk to come to. The first talk of 2025, we've changed the date on that. It was going to be the 3rd of January, but we thought that would be a little bit too soon, so into the new year. So it's now going to be on the 10th of January, and we'll have Professor Colin Snodgrass from the ROE, I think, about NASA's DART mission. So that should be good as well. That's what we've got to look forward to. But the main event this evening is we have how to be an exoplanet detector from Dr. Jo Barstow. So, Jo, if I can hand over to you, I look forward to hearing what you're going to say to us. Thank you.
Thank you very much. I'll just get on and share my slides and go full screen. That's working for everybody? Okay, perfect. Thank you very much for inviting me to speak to you this evening. So I'm going to tell you a little bit about what I do in my research, which is effectively being an exoplanet detective. It's trying to work out what's going on with the planets that are out there orbiting other stars. Now, my first slide is probably a little bit surplus to requirements given my audience tonight, because I imagine that since you're all here as members of an astronomical society, you're probably fairly convinced that we should study stuff in the sky. But just in case you weren't already convinced of that, the reason that we study exoplanets is actually because we can answer some really fundamental questions using our knowledge about planets elsewhere, about this one right here, the one that we live on. So, in order to understand how we got here, how our Earth and the solar system in which it sits got here, we have to look out of our solar system and understand other planetary systems. Obviously, a key motivator of this research is whether or not there are other habitable or indeed inhabited planets out there. Um, Cards on the table right up front, I find it very difficult to believe that this could possibly be the only planet in the entire universe that has life. What sort of life might be out there, I have no idea, but it would seem pretty odd if we were the only ones. But also, we're running right now a really quite ill-advised experiment on our own planet, which is called What Happens If You Pump Lots of Greenhouse Gases into the Atmosphere. If we want to understand how planetary atmospheres respond to different conditions, we'd be much better off just looking at other examples out there. So exoplanets in particular are really, really useful for helping to understand how atmospheric processes work. So the chemistry of atmospheres, dynamics and climate. And so there's a huge, vast amount of knowledge that we can gain from looking at planets around other stars. And of course, up until really quite recently, within my lifetime, this was all we had to go on. This was all we knew about planets. And we thought, okay, if our system is representative, then what we're expecting when we look at all the others out there is there's going to be some rocky things, and they're going to be quite close to the star. You'll see later on that close is a very relative term that we hadn't fully appreciated at this point. And then if there are things that are made of gas, they're probably going to be further out. And in our own solar system, of course, we've got 4 terrestrial planets, Mercury, Venus, Earth, and Mars. And then from about 5 astronomical units going out, we've got Jupiter, Saturn, Uranus, and Neptune. And within our own solar system, it immediately becomes obvious there's something a little bit special about the Earth. It has an atmosphere that's unique, and the uniqueness of that atmosphere, the presence of oxygen in particular, is inextricably linked with the fact that it is inhabited. It hosts life. So why does it host life and none of the other planets? Well, this is where the concept of a habitable zone starts to arise. So we think, as far as we know, that life requires the presence of liquid water to exist. So, by definition, any planet that is inhabited, therefore, must have the capacity to retain liquid water somehow. And the most basic statement is it the right temperature? Is it the right temperature for water to exist as a liquid? And that's related, of course, to how far away the planet is from its parent star. So, in our solar system, in the middle of the liquid water habitable zone, unsurprisingly, we have the Earth. Venus hovers around the inner edge, it's a little bit too warm. Mars hovers around the outer edge, it's a little bit too cold. So this is our sort of starting point as we started to explore planets around other stars. But of course, it's pretty difficult to observe a planet around another star. There's a good reason why we didn't find any of these until the mid-90s. And that's because, as you all know, being people who regularly look at the sky, stars are pretty hot and bright things, but they're a long way away, and planets are relatively small, cool, and faint. I'm sure none of you have attempted to observe Venus or Jupiter in the middle of the day, because that would be an absolutely ridiculous thing to do. The sun's there, you can't see them. So looking for something that is really small and cool and faint next to a much bigger, brighter, hotter thing a very long way away is like looking for a glowworm next to a lighthouse. For the majority of these objects, you simply can't do it. You cannot, with the current technology we have, see this planet. It's completely washed out by the light from the parent star. So if we want to find them, we have to be a little bit cleverer than just saying, well, let's look with a big telescope and see if we can see it. And in fact, the most successful ways so far of detecting exoplanets, they're both indirect methods, and they rely on observing not the planet itself, but its effect on the parent star. So those two very successful methods, the first one is what we call the transit method, which I've nicknamed the you're in my light method. So if a planet and a star line up just right, if the orbit of the exoplanet is exactly edge on or very close to from our viewpoint, then at some point, as it goes around the star, it's going to pass in between the star and us, and it's going to block a little bit of the starlight. For a Jupiter-sized planet around a sun-sized star, the amount of light that's blocked is roughly 1%. So that should give you an idea of the magnitude of this signal. It's about 1%. Obviously, as you go to smaller planets, it's going to block less light. So an Earth-sized planet orbiting a sun-like star would block about 1 part in 10,000 of the light. So if we're monitoring a star using a telescope like Kepler or TESS in space, or a ground-based telescope such as SuperWASP, when we're measuring the amount of light coming from the star as a function of time, then if we see a repeated little dip in the amount of light, then we can be fairly confident that we've detected a planet. And the size of that dip tells us the size of the planet relative to the size of the star. Another piece of information that we would also get for free, if you like, from this method is the orbital period of the planet, how long between those dips where the planet crosses in front of the star. So that's one way that we can indirectly detect a planet. The other one is the one I call the wobbly star method. The jargon term is the radial velocity method. So I'm sure all of you at some point sat in a physics or a maths lesson and got presented with some very contrived question on orbital mechanics, where you had a star and you had a planet going around it and you had to solve for the orbit. And you were probably told as well at that point, oh, it's fine, you can assume the planet doesn't have any mass, treat it as a test mass. And in that context, that's actually quite a reasonable thing to do, because the mathematics is much simpler if you do that. However, it is a lie. And we know it's a lie because we're standing here on the surface of a planet that very clearly has mass because we're gravitationally attracted to it. So when a planet orbits a star, what does not happen is the star just sits there and the planet goes around it. Actually, both of the objects orbit a point in space called the common center of mass. Now, because the star is much more massive, that point in space is very, very close to the star. Sometimes it's even actually within the body of the star itself, but the star will not be completely stationary. It's going to wobble around a little bit. And the amount of that wobble is related to the mass of the planet. So the more massive the planet, the larger the wobble of the star and the faster it will be moving as it wobbles. So if you've got a very close star and a nice massive planet, sometimes with a telescope like Gaia, for example, that's designed to measure very, very accurately the positions of stars in the sky, you can actually see a star moving against the further away background stars due to a planet. But most of the time, you're not going to actually be able to see the star moving. So we need a slightly cleverer way of working out that the star is wobbling. And we do that by measuring the spectra of the star. So if we spread out the light coming from the star into its constituent wavelengths and colors, then what you will see if you've ever done this, for the sun or indeed any other star, is that there are certain colors of the light from the star that are missing or fainter. And that's because there are gases in the outer regions of the star that absorb very, very specific wavelengths of light. They absorb these very clear fingerprints. And because we know very precisely which wavelengths a particular gas should absorb, then we would be able to tell if the star's spectrum has shifted. Now, the star's spectrum is going to shift if it's moving due to the Doppler effect, which I'm sure most of you have heard of. It's the effect that we experience on a fairly regular basis if you're walking down the street and a police car or an ambulance, something that's making a noise, goes past you. You'll notice that the pitch of the siren changes once the ambulance has moved past you and started moving away. And that's because when something emitting a wave, either a wave of sound or a wave of light, is moving towards you, the wave is compressed. And when it's moving away from you, the wave is stretched out. Now, when that happens with light, when the thing emitting light is moving towards you and the light is compressed, it gets very slightly bluer. And when the thing is moving away from you and the light is stretched out, it gets very slightly redder. It's a very, very subtle effect. The diagram on the screen is vastly exaggerated, But by measuring the light coming from a star and looking for those changes in the positions of those missing colors, those very specific fingerprints of different gases, we can infer not only the fact that the star is moving, but also how fast it is moving. The faster it's moving, the bigger that shift will be. So that's our other method of indirectly detecting the presence of a planet, by looking at the wobbling star. Now, if you've done both of these things, then you're already well on your way to understanding your planet. If you've measured the transit, then you have the radius, the size. If you've measured the radial velocity, the wobbling star, then you have the mass of the planet. And that gives you the density. Now, it's not perfect, but density gives you a rough idea of what your planet might be made of. For example, if you've got a big thing that's relatively low density, you can be pretty confident it's a gas giant. You also know from both of these methods how long it takes the planet to go around the star once, what the period is. That in turn gives you the distance between the planet and the star. And that in turn allows you to infer how hot the planet is, because that tells you how much light it's receiving from the star. So from measuring both of these things, we've actually got quite a lot of information about the planet. So as of today, we've done this for, I think it's coming up to 6,000 exoplanets now, and that number's ever increasing. And if you think back to the beginning of the talk, I described the solar system to you with rocky planets in the middle, gas planets on the outside. Well, that's not what they all look like. And in fact, the very earliest exoplanets we discovered were a real shocker, because they were Jupiter-sized things, not only close to the star, but very, 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 very close to their parent star. So the planets to date, which we've been able to study in most detail, are a class of planets called hot Jupiters. So these are anything sort of from Saturn to bigger than Jupiter in size. But typically they orbit their parent stars in a few days. Some of them even orbit in less than a day. One that's not on this diagram, WASP 43b, has an orbit of just 19 and a half hours. So its year is less than a day. Its year is the length of time it would take you to watch the Lord of the Rings and the Hobbit trilogies back to back. So these things are really quite extreme. And they're not what we were expecting. They're not actually intrinsically very common, these objects, but because they are nice and big, they are the easiest exoplanets to detect, and they're the easiest to follow up and do further measurements of. And this is an artist's impression of a few of these. This is a little family portrait of a few hot Jupiters, all of which have been studied by various telescopes. There's a range of different sizes, and there's a range of temperatures as well. So typical temperatures for a sort of middle of the road hot Jupiter is about 1,000 degrees C. But some of these, the ones in very close orbits around hot stars, they can get up to well over 2,000 degrees. So they're nothing like the planets in our solar system at all. But they're really fascinating for that reason, because they show what happens when you take an atmosphere and you put it into a really very extreme environment. We've also been able to find some slightly different planets that are also not found in our solar system. So super Neptunes, this is a really interesting case, and this is one that I've done more in-depth study of quite recently. So WASP 107 is often nicknamed the candy floss planet. It was discovered by the Super WASP survey, hence its name, and it's roughly Neptune mass, but it's nearly the same size as Jupiter. Now, if you know how much smaller Neptune is than Jupiter, you'd see that that's really quite strange. It's as if you'd taken something that's Neptune mass and you stuck a bicycle pump into it and you just inflated it and blown it up like a big ball. And we see this quite a lot, that planets that are very close to their parent stars get inflated because they're having a lot of heat deposited in their interior due to their proximity to the star, and that basically puffs them up. And these planets, again, they're really, really easy to detect, and they're super easy to follow up. And that's really, really exciting. But what about smaller planets? Well, one thing that we're noticing is that there's a class of planet out there that we don't have a representative at all in our solar system. And these
Oh,
are,
good.
sorry, and these are things that sit somewhere in between Neptune and the Earth in size. So we've got this very sort of clear dichotomy in our solar system between the small rocky stuff and the big gaseous stuff. But actually, there are loads of planets out there that are sitting kind of sitting on the fence. They're somewhere in the middle. And these are really fascinating to us because we just don't have a clue what they're supposed to be like. There's no example that we can look at here. But it also, these are tricky because when you get smaller than Neptune mass, knowing the density and knowing the temperature, it gives you it helps a bit, but it doesn't give you the full story. So I've got quite a busy diagram here on this slide. On the y-axis going from bottom to the top is the size of the planet, and then along the bottom going from left to right is the mass of the planet. Each of those little symbols is an individual planet that has had measurements of its mass and its radius made, and the little crosshairs are the error bars. Now, the lines on the diagram show where planets would be if they had a particular composition. So right up in the top left, we've got cold mixture of hydrogen and helium. So this is the stuff that's definitely gas. And then as you go right to the bottom right, you've got things that are made of 100% iron or some mixture of iron and rock, things that are more like Earth and Venus in compositions. This is the stuff that's rocky. But we've got this kind of ambiguous region in the middle where there are things that could have some rock and some hydrogen and helium, or maybe they're mostly made of water, or maybe they're a mixture of all of these things. And as you can see from the positions of those points on the plot, we don't know their mass and their radius precisely enough to be able to put them in one box or the other. So this is, who knows? Are they miniature Neptunes? Are they little gas giants? Or are they big super Earths? And this is something we really want to find out. We can't do this just by measuring the mass and the radius. So what do we do next? Well, clearly what we need to do is find some more information about these objects, but these are objects that we can't actually see. We can't just get a bigger telescope and zoom in. Well, maybe one day we'll be able to, but we certainly can't do that yet. So what we're going to have to do is make a different type of measurement, and we're going to have to use spectroscopy, but not of the star this time, of the planet itself. So I already mentioned that spectra of stars have these missing colors, these absorption lines that are due to different gases, different chemicals in the outer regions of stars. And the ones on our sun, the darkest, deepest ones are called the Fraunhofer lines after their discoverer. And they're mostly lines that are made of absorption by metals like calcium. Those are the purple ones. We've got iron, we've got sodium, which is that very specific orangey yellow color that those of you who remember what sodium street lamps look like, they'll be very familiar with that color. It's a very distinctive color. And also molecular oxygen going further into the red. And the reason you see these absorption lines is because light's emitted from what we call the photosphere of the sun, literally the sphere from which the photons emerge, and it passes through some cooler gas in the star's outer envelope before it gets into space. And when it passes through that cooler gas, then some of those colors will get absorbed. But of course, there's no reason that can't happen as well when you've got your planet transiting in front of your star and passing in front of it. And of course, it does happen when you've got your planet transiting the star. So if instead of thinking about now light passing through the outer layers of the star, we think of the light that's already emerged from the star and the planet sitting in front of it, well, the middle bit of the planet, that's going to be opaque at every wavelength. That's going to just block all of the light. But the atmosphere of the planet, that shell of gas that surrounds it, that's going to be only opaque at certain wavelengths. It's going to be semi-transparent. So it's going to let some light through, but not all of it. And that light's therefore going to emerge with these fingerprints of the different gases that are present in the planet's atmosphere. So if when our planet is transiting now, we don't just look at all of the light coming from the star, but we look at light at different wavelengths, we're going to see something quite different. So if we look at light either side of the sodium absorption feature, then you'll measure a transit of a particular depth. It'll probably be about the same. But if we then look at what happens in the middle of that sodium absorption band, that very specific orangey yellow color of light, we will see a deeper transit if the planet has sodium in its atmosphere, because it's going to block more of the starlight. The planet's actually going to appear to be physically bigger. So I'm actually going to show you now, this is a real observation that's done exactly that. This is from data from the Very Large Telescope. This is a ground-based observation. It's an optical observation of a hot Jupiter called WASP 96b. And what's being shown here is basically how much light the planet was blocking from the bottom to the top, and then bluer light is on the left, redder light is on the right. And you can see that there's this very distinct ramp up towards the center of this sodium feature and then a slope on the other side correspondingly. And the red line underneath is a model that was fitted to the data points. The data points are the black blobs with the whiskers on. And it's not just sodium. You can actually see there's some little secondary bumps here. There's one that we've attributed to lithium and one that's attributed to potassium. And to give you an idea of how big this effect is, the planet actually appears to be about 4% larger in the middle of that sodium band. This is quite a puffy atmosphere, so that's quite a big signal. So you might think, oh, that's great, 4%, that's quite a big signal, but it's 4% of the 1% of the starlight that's blocked out. So the signals we're trying to measure here when we're looking at what's in these exoplanet atmospheres, it's a few parts in 10,000. So they're quite small signatures, and therefore we need some really quite good hardware to do this. How fortunate for us then that coming up to 3 years ago now, something called the JWST launched into space on Christmas Day. Probably the most nervous I've ever been on Christmas Day. Was watching that launch. And it's the largest space telescope built to date. It has a 6.5-meter gold-plated mirror with a tennis court-sized sun shield. And most importantly for the science that I do, this is an infrared telescope, not an optical telescope. And that's useful for me because whilst I'm interested in absorption by sodium and potassium, but actually what I really want to know about is absorption by molecules. I want to know what the molecular signatures are in these exoplanet atmospheres. And if I want to look at molecules, then the infrared is the wavelength range I want to be in, because that's where all the molecular absorption features are. So we have now access to many, many, many more species than we did prior to the launch of this telescope. Hubble got us atomic species and a bit of water vapor. JWST gets us everything really that we could possibly want. So this is one of the very earliest spectra obtained using JWST of a hot Jupiter called WSP39b. So it's a pretty standard hot Jupiter as these things go. It has a temperature of about 800 degrees C. It's Saturn mass, but roughly Jupiter size. So it's quite a fluffy one. It's quite inflated. And if you look at the very left-hand side of that plot and the insert, that sharp spike on the left-hand side, that's the sodium feature again. That's what you were looking at in the optical spectrum I showed you before. But then we've got a ton of other bumps and wiggles. So how on earth do we tell what's actually there? It's quite tricky. It's a little bit like doing an EFIT. So whilst atomic species have these quite distinct and quite narrow features, molecules tend to be a bit messier. So they tend to have a lot of different lines that all overlap with each other. So you can't just very easily just look at the spectrum and say, okay, well, yes, well, that is clearly water, that is clearly carbon dioxide. So this is actually what I spend most of my time doing, and it involves, I'm afraid, an awful lot of cursing at my computer. But I generate basically lots and lots of different iterations of a model atmosphere for a particular planet and simulate the passage of light through that atmosphere. And that gives you the predicted spectrum for that particular combination of gases. And then basically I compare it with the observation and see which ones worked and which didn't. It never works as beautifully as this particular example, where I think you can all see that the green model and the green spectrum is the one that actually matches and the others are missing bits or have bits that shouldn't be there. What we generally end up with is a family of models that produce a reasonable match. And that gives us a statistical estimate of what gases are present and how much of each gas is present. So this is, again, the spectrum of WSP39b, but this is with an extra observation that we took subsequently added on the right-hand side. And this is my jigsaw, which is actually a real jigsaw. I made this for the Royal Society summer exhibition, and the kids really quite enjoyed it when they came to our stand, putting it together to try and work out what was there. So this shows how each gas contributes to that overall spectrum and how much light the planet blocks. So what we've got here in the blue, we've got lots of water vapor. You might possibly think that's a bit strange, but it's not. Water vapor is ubiquitous. It is absolutely everywhere. It's a really easy molecule to make. It has absolutely no relationship really to whether a planet has a liquid water ocean or anything like that. You see this in nearly every atmosphere that we've observed. So water vapor expected. That has lots and lots of absorption features. So it's quite a dominant absorber. The pink is carbon dioxide, so you can see that has one very, very distinct feature right in the middle and a couple of other features. Then we've got the little green chunk, that's carbon monoxide. That's heavily overlapped by both CO2 and the water, so that's quite difficult to do. And then the yellow stuff is sulfur dioxide. And that made us all go, what? What is SO2 doing here? Water vapor, yes, we expected that. Carbon dioxide, carbon monoxide, yeah, 100% expected. But prior to looking at this data set, we had models that were basically generated on the assumption of, okay, if you have a gas giant that's mostly made of hydrogen and helium with a little bit of oxygen and a little bit of carbon, and you warm it up to this temperature, what gases do you expect to form? What chemistry do you expect? And those models predicted H2O, CO2, CO, and not SO2. They instead predicted a different sulfuric gas called H2S, dihydrogen sulfide. And that's because this is an atmosphere that's mostly hydrogen and helium. There's a bit of oxygen, but not a huge amount of it hanging around to react with stuff other than water vapor and carbon dioxide. So that this very, very early observation from JWST immediately made us sit up and go, okay, we've got something wrong. We don't understand these atmospheres as well as we thought we did. So we had to do a little bit more work, and we realized that we were neglecting a photochemical process that's ongoing in this atmosphere. So what we think is happening is that ultraviolet photons from the star, I mean, this planet is orbiting in an orbit of just a few days. It's very close to its star, so it's going to be receiving an awful lot of ultraviolet radiation. And those ultraviolet photons, they break up the very abundant water molecules in the atmosphere. And then reactions can happen between the dihydrogen sulfide that we expected to be there and the products of that what we call photodissociation. Something's broken up by photons, and that produces the sulfur dioxide. So we learned something brand new about how these atmospheres work from this very, very early observation, which was really exciting. So there's a huge amount that we can learn from JWST and from its observations of these exoplanets. Now, WST-39b, that's a gas giant, it's a hot Jupiter. We're observing lots of those with JWST, and they're all really interesting because they're so different from what's in our solar system. But right at the other end of the scale, we've got systems like TRAPPIST-1. And I expect many of you have heard of TRAPPIST-1. It's one of the most famous exoplanet systems. And the reason it is so famous is that it's a system of 7 rocky worlds orbiting very close to a star that's in our near neighborhood, although it's a much, much cooler star than our sun. And of these 7 rocky worlds, the planets in the middle, E, F, and G, they're all possibly sitting in the liquid water habitable zone of their parent star. So this is a system that is going to be heavily investigated with JWST, because obviously we'd really love to know what the atmospheres of these 7 rocky planets are like, and if any of them are in any way similar to the ones in our own solar system. So one thing that we could do potentially is to look for signatures of something like ozone in the atmosphere of one of these planets. Ozone is a useful gas because it's heavily related to the presence of oxygen. So the oxygen that we breathe is O2, 2 oxygen atoms stuck together. Ozone is O3, 3 oxygen atoms stuck together. And you don't get the kind of large quantities of ozone that we see on Earth unless you're in the presence of an atmosphere with a lot of oxygen. So this could be potentially a way of identifying an atmosphere similar to Earth's if we saw an ozone signature. However, the smaller the planet is, the harder this technique is. So I talked earlier about the signals for a Jupiter-sized planet being about of order 1 in 10,000, measuring these little bumps and wiggles. It's closer to 10 parts in a million for an Earth-sized planet like this. That's really, really close to the absolute limit that JWST can do. So these are not real observations. These are simulated observations of what TRAPPIST-1e, the central planet in that system, would look like if it was observed with JWST. But if it was observed 100 times over, and then all of those observations were added up together to produce that signal. So that's 100 different observations, and you can still see that it's really quite a noisy measurement, and it would be quite difficult to do. And I can tell you that 100 observations is beyond what we can expect to get on this telescope, simply because it's a multi-purpose observatory. It's not just for looking at exoplanets, it's for all of astronomy, and this would be a huge chunk of its available time. So it's probably going to be challenging to get this kind of observation for those planets. That's not to say we can't say anything about them, but it's going to be very, very difficult. So hot Jupiters, easy, low-hanging fruit, really interesting, definitely not habitable, of course. And then the ones right down at the other end of the scale, the TRAPPIST 1e and its ilk, they're really, really challenging to observe. But what about these planets in between? And I told you earlier on that these are really fascinating because it's the in-between worlds for which we have no analogue in our own solar system. And we'd love to find out more about them. So one of these objects is a planet called K218b, which is another one that you may well have heard of because it's had quite a lot of media attention in the last year or so. So K218b is a classic example of one of these. Is it a small Neptune? Is it a big rock? Ambiguous planet. So it's got a mass of just over 8.5 times Earth's. It's got a radius about 2.5 times the Earth. And it's right in the middle of this ambiguous region. Could it be rock with a bit of hydrogen and helium? Is it a water world? You can't tell until you have a spectrum. And this has been observed with JWST in the last year. And this is its transmission spectrum. So what do we see? Well, lots and lots of methane. So this series of bumps that you see sort of getting gradually wider and wider coming from the left, that's methane. And we get some CO2, that's expected. You might be looking at that and thinking, okay, well, clearly it's not a water world because there's no water. Actually, this is perfectly compatible with it being a water world if the water is actually liquid and on the surface. If the water is condensed and it's a liquid, then you would not actually expect a huge amount of it to be visible in the top of the atmosphere in gaseous form. So this is completely consistent with it being a water world. And the thing that really got the media attention is this chemical called DMS, dimethyl sulfide, of which there is a really, really small hint that possibly maybe it might be there in this spectrum. And this generated a huge amount of excitement because DMS is produced on Earth by little creatures living in the ocean. So, of course, immediately, in particular, the media attention went to, oh, this is the picture of this planet. It's just a gigantic water ocean with lots of little microorganisms floating around. But of course, it really isn't as straightforward as that. So computer simulations that were performed by another team showed that a mini Neptune atmosphere was really just as consistent with the observations compared with an ocean life scenario. So then you kind of have to ask yourself which is more likely. And I mean, we don't really know. We don't really know what's going on with these planets, but this leads me on to sort of the final bit of my talk, which is a little bit more philosophical, because I think this is actually a really interesting problem that's facing astronomers who work in the exoplanet field at the moment, but particularly it's challenging us as science communicators. And it's the question of, can we really detect life on an exoplanet at the moment with the equipment we have? Could we ever be certain enough? So I hope that so far I've been able to convince you that we are capable of detecting and measuring atmospheric gases, but also that it's pretty difficult to do for smaller planets. But the other side of that is that even if we are super confident about the measurement we've made and we say, yes, we've detected this gas and we are absolutely certain it's here and we think there's this amount of it, how sure can we be that it means what we think it means at that moment in time? I think that's harder. So to go back to my first example of this with this hot Jupiter WASP 39b. Now, no one was ever going to look at WASP 39b and go, oh, there must be life because we've seen something that doesn't make chemical sense. But well, we did see something that initially didn't make chemical sense, and then we went back to we went back to the books and the lab and the computer and went, actually, no, this is fine. This makes perfect sense. We were just missing one actually quite obvious process. So I think that looking at these planets and looking for Earth-like planets and evidence of aliens, I think we all want to find it. I think it's actually quite a human thing to want to do because I don't know about you, but I find it a little bit uncomfortable I would find it very uncomfortable if I thought that this was the only planet in the universe that had life on it. It would seem so strange and so unlikely. So I think we really want to find aliens, but we can and we very often do get things wrong if we don't have all the information that's available. One of the examples I really like to quote is which Patrick Moore wrote about very nicely in his book about Venus that he wrote in the middle of the last century, is the early 1900s view of what Venus was like. Because by that point, astronomers knew that Venus was closer to the sun than the Earth was, and therefore it was going to be hotter. But they had no idea that it had an atmosphere dominated by carbon dioxide and a gigantic greenhouse effect. So they thought it was going to be a little bit like Earth in the Cretaceous period, a bit warm and a bit humid, and maybe there were some dinosaurs wandering around, who knows? But actually, we know now that its atmosphere precludes, well, almost certainly precludes the existence of life. It depends. The phosphine on Venus is a whole other story that I won't get into, but we could perhaps talk about afterwards if anybody's interested. And I really like this webcomic from XKCD that talks about the relationship between caution and evidence in assessing this sort of claim. And I think the middle panel is a really good way to go. So yes, they might be produced by life, but it also could just be weird chemistry with another process that we don't understand. So I'd be quite interested to hear, perhaps at the end of the talk, what would convince you? What would be the burden of proof that you would require of aliens elsewhere in the universe? And I think it's actually really quite difficult. And so personally, cards on the table, I think that with the current technology we have, we could not achieve sufficiently high evidence to be able to claim that we had detected alien life. We could certainly talk about interesting hints, but I think claiming a detection would probably be going too far. That might change in the next few decades with things like the Habitable Worlds Observatory coming online. I think at the moment that's where we are. Okay, I'm pretty much at the end of my talk, so I just want to recap the tools that you need to become an exoplanet detective. So you need to have measured the transit of a planet to have learned its size and its period. You need to have measured its mass by looking at the what star wobbling around and measured the radial velocity of the star. You need a spectrum, and you need some models that enable you to interpret that spectrum that tells you the atmospheric composition of your planet. And all of these things together gradually get you close to starting to understand one of these fascinating planets. And we're starting to sort of really dig into this now with JWST. JWST has made it apparent just how much we were only scratching the surface before. So over the next few years, JWSTs should have another 15 years of operation, given how successful its launch was. We're going to see so many more of these objects with beautiful spectra, and we'll start to really understand exoplanets as a population more. So I'm really excited for the near future, and I feel very fortunate to be working in this field at this point. So I'm very happy to take questions and discuss the philosophy of whether we've detected aliens or not with you. Thank you very much for your attention and for listening. That was how to be an exoplanet detective.
Well, thank you very much for that, Jo. Can we thank Jo before we go to questions? Thank you. If you have a question for Jo, can you put your name in the chat and I'll read you out. One question I have, Jo. So obviously JWST is the telescope you want to use, but there are other missions up there. So Cheops is up there already, and Ariel's coming up. They're not going to have
Yeah.
the resolution of JWST, are they? What will they tell us that we haven't got already then?
They're both really valuable in their own way. So Cheops is more like Kepler and TESS in the sense that it's a very precise transit instrument, but it's a white light instrument, so it's not for spectroscopy. But it has the capability to get really, really precise light curves. That can be very useful for verifying planets that may have been detected by TESS. So that's been a really successful mission, and it can do some really good stellar science as well, actually, because you can get such precise light curves. And then Ariel, so I've been involved, I didn't talk about it, but I've been involved in Ariel for 10 years now. So from very early on in the conception of the mission. And you're right that it won't have the precision of JWST. The mirror is smaller, but it has other advantages. So aerial gets the wavelength range right from half a micron all the way out to 8 microns in one go, which JWST can't do. That needs more than one observation to get that range. And the other thing is it's a dedicated exoplanet mission. So one of the things that I really hope it will do, that we're discussing as part of the team at the moment, is that it could do lots of measurement of what we call phase curve measurements. So that's not something I talked about here, but for some planets, the ones that are particularly close to their parent stars, if you can observe them throughout an entire orbit, so continuously stare at the star for a whole orbit, what you actually see is the hotter day side of the planet that's being cooked by the star rotating in and into view and then out of view again. So you actually see the planet's emitted light on top of the star's light. And using a phase curve measurement, you can not only get the light that's emitted by the planet's day side, but you can actually get what's emitted by the night side as well, even though it's very, very small. And that tells you an enormous amount about these planets. And you can do that spectroscopically. I'm not just talking about doing this in white light. I've done this for an ultra hot Jupiter called WST-121b with JWST, and it's absolutely stunning data set. But Ariel will have the time to do this for lots and lots and lots of planets. And that will be really exciting because that gives you just an unprecedented level of detail.
Yeah, that's good. A few of us are actually involved in Ariel indirectly with the Exoclock project. So
Yeah, okay, that's great, isn't it? I think that's a really good way of getting citizen science, and it's really critical actually having those ephemera, having those. I never know how to say that word.
yeah, right.
Ephem Ephemerides, or yeah, having that's it's so important because if you miss the transit,
Hmm.
then you miss the transit. You need to know when that thing is going to transit. So that's brilliant. I'm really pleased you're involved in that.
We have quite a few questions here. Mike Christie, do you want to ask your question?
Yeah, great talk. Thanks, Joe. I was really interested in your calibration of the models to spectra, and there's two parts to that. One is what I call parametric uncertainty. You don't know the composition of the atmosphere. But the second is something that you showed, which is you were missing a bit of physics,
Interesting.
so your photochemistry. So to what extent do you cover that, which I label as model uncertainty, as well as the parametric uncertainty when you're fitting your curves?
I mean that's basically that's pretty much the bread and butter of what I do. That's a really good question, and it's really hard. So the kind of models, so the model that I was talking about there that was missing the process, that was not the kind of model I run. So that's a one-dimensional thermal chemical equilibrium model. I use a different type of model, which is much simpler in that it contains very little embedded physics apart from radiative transfer. So everything is basically a knob that can be twiddled.
Mhm.
And so that is good in one sense because it means so those kind of models would give you that SO2 quite easily. As long as you thought to include it in the set of gases you were using, it would go, oh, look, here's SO2. The downside of that, of course, is that you can end up with scenarios that do not actually make any sense at all.
Mhm.
At which point you have to go back to those more physics-based models and try and find out a sort of compromise or at least a bit of critical analysis, if you like. So the way that we do it really is to try and use as many different approaches as possible and to try and be as agnostic as possible at the outset. So the kind of tools that I use are sort of inherently quite agnostic. So we use very broad priors on the abundances of gases over several orders of magnitude. We try not to influence the solution but via our own prior assumptions as far as possible. I mean, it's impossible to divorce yourself completely from that, right? Because at some point, you always have to make a choice.
So by using priors, you're using a Bayesian approach then?
Yes. So I use nested sampling to do the inversion. That's what most people use in the field now. Some codes still use MCMC. Nested sampling is a little bit more robust to having sort of multimodal posterior solutions. And it doesn't tend to get stuck in local maxima quite so easily.
Okay. I'm sure we could talk. I'm sure most of the people are not so into that, but we could chat later on that or something. But yeah, great. Thanks.
Yeah, no idea what that was all about, Mike, but yeah, it sounded very interesting.
I'll happily explain it to you sometime, Mark.
No, thanks, Mike. Sam, you have a question. Do you want to ask your question?
Oh yeah, I would love to ask about Bayesian analysis, but my question is not about that. So you mentioned about the world world K218b,
Yeah.
which has another name called Haitian, if I'm not
Yeah,
mistaken.
that's right. Yeah.
So I had to read about this for the past week because it's a pretty popular topic, and because the new JWST spectrum showed a lot of CO2 gas within its hemisphere, and I know that this kind of planet, if it's a Haitian world, it's meant to be covered by like a some sort of thick amount of atmosphere, and there's water ocean beneath it. So I'm just wondering, like, because CO2 is very good greenhouse gas, and I know these kind of planets are quite close to their host star. Won't this like greenhouse effect kind of like build up, and this planet gets sort of like towards the hot end, so it's not that habitable? So I just want to ask about your opinion on like, what do you think about this kind of Haitian world? Is it like a physical model, or it's just like it's a model?
Yeah. There's a lot of debate about this, and actually, it's not the CO2 that bothers people about. So you're absolutely spot on that the greenhouse effect and the degree of the greenhouse effect on K218b could render it uninhabitable and remove that liquid water ocean. But actually, what concerns people is not the CO2, which is only a trace gas. It's actually the hydrogen and helium, which is the bulk of the atmosphere. Because if you have enough of that, that's actually a pretty good greenhouse combination as well. And so this is a debate that is currently raging within the community, whether this thing can have a liquid water ocean or not. 50% of the people say, oh, yeah, sure, it can. The other 50% are saying, absolutely no way. It's got too much hydrogen and helium. The greenhouse effect is going to dominate. And the jury is still out.
Right, okay. I have a presentation on this topic in like 4 days. So, oh, thank you.
Yeah, thank you. Nigel, any questions?
Yes, thanks very much, Joe. That was a fantastic presentation. I just had really a couple of questions. One was, given that the transit method of detecting exoplanets is essentially a line of sight method, everything has to line up to where we're looking from, and the other method is dependent a lot on the size of the planet and so on, and how far it is from the star. Do you think there's a lot of planets out there that we are missing, and do you think we'll ever be able to find those? And my other part of that question was, given we now have 6,000 or so planets discovered, with that size of population, are we starting to see patterns in planetary systems? And have we found any planetary systems that look like ours, with inner rocky planets and outer gaseous planets?
Those are all really good questions. So to answer your first question, yes, absolutely, we're missing loads of targets. Our methods are completely biased. However, it's also quite easy to calculate what that bias is. So the line of sight bias that you mentioned, but also the bias to do with the size. So I think the Kepler mission was particularly good for this. So because Kepler observed so many planets in one very specific bit of space, they have very good idea of how complete their sample was based on what they know they should have been able to detect. And that's what led to the sort of quoted statistic of one planet for every star on average. So although, we obviously haven't measured anything close to one planet for each star we've looked at, that probably is pretty close to the average, given our understanding of how complete our surveys are. So we are missing a lot. So the ELTs and things like Habitable Worlds Observatory that are coming up in the next sort of 2 decades, that's going to start to change the game for types of planet that we're completely insensitive to at the moment, but those will be much better suited for. So those are I haven't talked about direct imaging at all, but what we can directly image some planets if we have something called a coronagraph that basically is a physical stop in the middle of your image. So if you center your image on your star, but you put a physical stop in your telescope optical path where the star is, you block the starlight, and that means you can see the things around it if they're widely separated enough and bright enough themselves. So that's been done for young gas giant planets so far. But habitable worlds in the ELT will start to be able to push down to cooler and smaller planets as well, using that same technique. And that's a completely different system architecture, because that's much better suited to completely the opposite case where you've got a face-on system. So there are going to be ways to sort of address some of that bias as we go into the future. I'm trying to remember. Sorry, what was your second question?
I just wondered whether, since we're discovering more and more planets, whether we've now got a sample size of
patterns.
where
Yes.
we can start to see patterns in planetary systems.
Yes, we are starting to see that. So we're starting to see, but again, it's still a biased sample. So a lot of the rocky systems we see, they're orbiting stars that are not like the sun, that are much smaller and colder. But we do repeatedly see these sort of resonant chains of rocky planets very close together, like TRAPPIST-1. So that seems to be quite a common occurrence. Hot Jupiters tend to be on their own, which, at least as far as we know, I mean, we're not sensitive to things that are too far out, but as far as we know, most of them are solitary, which maybe says something about how chaotic their path was to get there. They can't have formed that close to the star. We know they've migrated. It might have been a bit messy as they sort of wiped their way through the inner system and got that close to the star. So we're definitely starting to see patterns in this architecture. And we're not, I think we have seen a few systems that have smaller things on the inside and bigger things on the outside, but certainly nothing yet that is truly analogous to our own system. The closest, I think, which only has the gas giant component, is one of the directly imaged systems called HR 8799, and that has 4 planets at not exactly the same, but similar sorts of distances to Jupiter through to Neptune in our solar system. But they're young, so it's like a snapshot of the outer solar system as it was early on in its evolution.
Thank you.
We have just 2 more questions if you're still okay, Joe, to answer those.
Yeah, that's fine.
John Briggs, do you want to ask?
Oh, hi, thanks, Joe. Excellent talk. Actually, Nigel beat me to it, most of the questions. Just remains to ask, if you have a planet like the Earth at the size and the distance from the star, how close are we to detecting an object like that? It's very small relative to the sun, and gravitationally has no effect to speak of, I guess.
So the biggest challenge, so the obvious method for that would be the transit method, and the biggest challenge is actually, it's not so much the size of the dip, it's actually the alignment issue. The further away you go from the star, the less likely it is to transit, because the range of angles is it will still transit is much smaller.
It's extremely unlikely, I would have thought.
It's very unlikely. So you'd need a big sample. And this is one of the things, the Plato mission, which hasn't come up yet at all. So this is an ESA mission that's going to launch in the next 2-3 years, actually. And this is another transit search mission. But the aim of Plato specifically is to look for these longer periods transiting planets that would be equivalent to the Earth around the sun. So in the next few years, we'll start to detect those. And then going even further forwards, the mission that's just ramping up in the US that I've actually been involved in one of the sort of early sub-working groups for is the Habitable Worlds Observatory. So this is the sort of next big flagship that NASA are planning. And this will be basically like a very, very, very big Hubble in space. In terms of wavelength coverage, it will be ultraviolet, optical, and a little bit of infrared. But it will have a coronagraph. And the aim of that is basically what it says on the tin. It will be able to directly image an Earth around a sun.
Okay. Even something as small as the Earth.
Yes. That's what one of the biggest design drivers is.
Wow, that's quite amazing.
Yeah, so
That'd be amazing.
It will be a very big telescope. It will be a massive engineering feat. This thing we're looking at sort of 2040s for the launch of this. At the moment, I mean, given how much JWST slipped, goodness knows when actually. Hopefully it won't be delayed for quite as long, but
Eh?
2016
Interesting, yeah. Okay. We have one last question from Jim Barron. Do you want to ask Jim?
Hi, Joe. Thanks for the talk. I was thinking about the data you had for the TRAPPIST-1 system, so where you're trying to figure out the atmosphere of the rocky planets. Looking at the size of the error bars and trying to fit the curves to that, I was wondering a couple of things. What percentage of the atmosphere does a gas have to be to even show up from the noise in the system? And also, how complex molecules can you detect? Because I think methane was the most complex one you're showing. Are they just limited that they're not in the spectrum that you can see, or are they not considered just now?
that's it. That's a question that has quite a lot of different parts to the answer. So in terms of how much of a gas has to, it depends on the gas basically, because some gases have much stronger intrinsic absorption features than others. It also depends on lots of other things like the temperature of the atmosphere, whether there are clouds. If there are clouds, you're pretty much stuffed if they're high up enough, because that will just wash out everything. You'd have to then have a very strong, very narrow absorption feature to sort of stick up above that. And also what the bulk composition of the atmosphere is. If you have something that's mostly nitrogen compared with something that's mostly CO2, CO2 is harder because CO2 is heavier than nitrogen, and that compresses everything a bit more. It flattens everything and all those features. So it's quite hard to make a statement about exactly how much. I think you'd probably be looking at maybe 100 parts per million would probably, for an Earth site like planet, probably you'd be looking at that kind of abundance to have much chance of seeing anything, at least with JWST. And then if to talk about the more complex molecules, that's a multifaceted problem. So one aspect is that they're not likely to be so abundant. But also our data for understanding their absorption, particularly this wouldn't be so relevant for an Earth-like planet, but particularly for sort of higher temperature applications, that is actually not very complete. So then we have a modeling problem because we don't actually know exactly what we're looking for. And there's there are whole labs worth of people who are actually working on solving that exact issue. Some of them doing it through laboratory work, but also many people actually doing it via quantum mechanical simulations of molecules, because some of this stuff is very, very challenging to measure in the lab. So a lot of the absorption data we use now is not actually measured in the lab, because we're trying to work out, what methane looks like when it's absorbing at 2,500 Kelvin. You can't do that in the lab. That's simply impossible. So it's based now on quantum mechanical simulations of how this molecule should behave at this temperature.
Thanks very much.
Come to the end of the Zoom questions. Anything on YouTube, Will?
No, nothing on YouTube. Excellent talk, Joe. Marvelous.
Well, thank you again, Joe. That was an absolutely brilliant talk. Sort of thing we love here. So I think we thank Joe again for his talk.
Yeah, thank you for having me.
That's it for tonight. Our next talk is on the 6th of December, and that will be a hybrid talk in person at the Augustine United Church and on Zoom and on YouTube. It'll be Dr. Rebecca Higgett on the early dial. Historical talk. That should be good fun as well. So thank you very much, Joe. Thank you very much, everyone, for joining us, and we'll see you at the next meeting. Good night.